Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really interesting hangout planned for you. We are going to be talking about galaxy collisions, and in particular, one galaxy collision that had some strange, unusual, bizarre things in it. And we've got the astronomers here to help us decipher what they're looking at and what they are. We'll talk about galaxy collisions and where they occur, and in particular what this strange feature that they found might actually be. And so we will be starting that discussion in just a minute, but before I start with the introductions, I want to say we're hoping you guys will leave us comments and questions on the Q&A app, which we're watching, the Hubble Hangout hashtag on Twitter. We're also we're looking at comments on YouTube and G+. So we hope you'll interact with us and let us know what you think. Give us some questions, and we'll get to those hopefully throughout the Hangout. With me to help with this Hangout are my two good friends and colleagues, Dr. Carol Christian. She's the Hubble Space Telescope Outreach Astronomer, and also with me is Scott Lewis from knowthecosmos.com, and he's just getting started doing all kinds of cool things with the Natural History Museum in Los Angeles. So welcome, Scott. Welcome, Carol.
Hey.
How's it going?
Awesome.
We ready to rock?
Ready to rock!
Do this.
Okay, so today, galaxy collisions. With me well, I've got three astronomers who've been using the Hubble Space Telescope to look at these things. I have, first of all, Dr. Grant Tremblay. He was, at the time the press release came out, was working at the European Southern Observatory. Now he is the NASA Einstein Fellow at Yale University. Welcome, Dr. Tremblay.
Hi, guys.
Also is Jane Rigby. I'm just doing this from left to right as they appear on my screen. Dr. Jane Rigby, she's an astronomer at NASA Goddard. Hi, Jane.
Hello.
And finally, we have Karen Sharon. She's a professor from the University of Michigan.
Hi.
Welcome, guys. Okay, galaxy collisions. You guys have been using the Hubble Space Telescope to study these things. Is this what you've always been doing, all three? Is this your primary area of research? Grant, I'll start with you.
Well, first of all, I work on clusters of galaxies in general, namely star formation and black hole feedback, so energy feedback from black holes. But on this particular study, I was very lucky to be sort of a guest in Jane and Karen's house, because this is their data, this is their amazing program.
Okay.
They can tell you a little bit about it.
Okay, so wait a minute now. You said feedback. Say that again, feedback from black holes. What kind of feedback?
Yeah, so I work on brightest cluster galaxies in the center of rich clusters of galaxies. So clusters of galaxies are giant groups of galaxies, which we'll talk about today. And I work on the galaxies in the very center of them. And many of these galaxies have what are called active galactic nuclei, so accreting supermassive black holes, billion solar mass black holes. And when you dump a lot of matter into a black hole, it liberates tons of energy, and I work on what effect that energy has on its ambient environment.
Good, because I wanted to clarify that, because it's a little counterintuitive. People think of black holes as just grabbing and sucking everything in, but they actually throw things back out again, too. So that sounds like an interesting hangout in and of itself. So that's great. Okay, how about you, Jane and Karen? Let's start with you, Karen. Is this your main area of research? Have you always been involved in galactic or galaxy clusters and collisions?
Well, I've been involved in galaxy clusters for as long as I've been in astronomy, but not necessarily what we're talking about today. So
Okay.
my main interest is in a phenomenon called gravitational lensing, which is the bending of light around very massive objects.
Right,
And
we're going to get to some of that in a little bit. So
Right.
we got some areas, we got some graphics for that, too.
Right, so like Grant said, we have this amazing project with the Hubble Space Telescope looking at galaxy clusters, which are very, very massive, so that they bend the light of galaxies behind them. And this is our main program or main science with this great program. However, sometimes when you take a lot of pictures with a space telescope, you find some things that you do not necessarily expect. And this object that we're talking about today is one of those things.
Great. Okay, Jane. How about, so give us a little background on what your research interests and background.
Sure. So I'm interested in galaxies of all kinds, whether they're forming stars or not, especially those that have black holes in their centers that are currently feeding and fueling, like Grant was talking about. And recently I've gotten very interested in studying galaxies using gravitational lensing, which we'll talk about. And so Karen and I and our colleague Mike Ladders and several other astronomers have this big program to study galaxy clusters that are really good gravitational lenses. And kind of by that's why we took this data. So it's one of 37 clusters that we wanted to study the background galaxies that are getting lensed. And this was a case, this paper that Grant, we invited you to our house. I like that. That came from was we were looking at this cluster and saying, wait a minute, what's that? Right? What is that? What's going on in the sun?
I remember we really did do this.
Right? Yeah, pores, right?
Okay, so
Right?
let's go ahead and put up a picture of the cluster we're talking about. So you guys looked at this cluster known as SDSS, which I think stands for Sloan Digital Sky Survey,
Yep.
J 1531 plus 3414. I just love these names. So here is a picture of the galaxy cluster itself. How many galaxies are in this thing? Do we know?
Do we have to count right now?
Yeah.
More than
No, I'm
one.
just wondering if anybody knows.
More than one
We
and
don't
less
know,
than
but-
infinity.
Okay,
One, two, three, four.
It's quite.
So first of all, when you look at this picture, you can notice that some of the galaxies look sort of the same. They look like they're yellow or orange, and they sort of have about the same color, and those are all cluster galaxies. Other galaxies that can be smaller or larger have different color, and they would typically be either in front of the cluster or behind the cluster. So when you count galaxies, please only count the yellow-orange ones.
Okay. All right. So the first thing that strikes me when I look at this is obviously, like you said, there's these orange ones, these big roundish sort of oblong-shaped galaxies in here. And then there's all these other squiggles all the way around it, these bluish kind of squiggles. Can you describe to us what's going on here? What are we looking at as far as the colors and the shapes?
Right, so the orange galaxies, those oval-shaped galaxies, those are members of the cluster, which has probably a couple hundred galaxies in it. Some are larger, some are smaller. Besides those galaxies, there's a whole bunch of dark matter, which we can't see, kind of by definition.
Right.
And all that mass makes this cluster a very good gravitational lens. And all those round-shaped things that you see there kind of look like arcs, and this is what we call them. Those are background sources that are being bent and distorted by the mass of this cluster, or more correctly, the light from those galaxies is distorted, and we see them as those archy shapes.
So the orangish blobs, those are actually in the foreground. Those are between us and the bluish stretched out shapes, right?
Yes, exactly.
Okay, so does the color mean anything? I mean, I know that these orange ones are orange and they're kind of blobby looking, but everything else seems kind of blue. Does that signify anything?
Yes, it does.
Okay. Can you tell us what it might
I'm
be?
waiting for Jane to.
Oh, well, I was going to.
Okay, I should have directed that directly at someone. How about
Okay.
you, Jane? You answer that one.
Sure. So the color tells you a lot. Just looking at that image, you can see that the yellow, orangey, blobby galaxies aren't forming stars. They're done. Clusters of galaxies are these extreme environments that seems to accelerate the evolution of galaxies.
Okay.
And so when we look at a cluster of galaxies, they look yellow or red like that because they're done. They're not forming any stars. They have their stars that have already been formed, and that's it. No new star formation.
Or
Whereas-
so we thought.
Or so we thought, right?
Or
That's
so
the
we thought,
general
exactly,
picture.
yes.
Foreshadowing.
That's why we're here today.
Okay.
So, and then those background galaxies are forming buckets of stars, and that's why they're blue, because hot new stars are blue.
Okay, so let's before we get too much into the details of this cluster, let's go ahead and talk a little bit about gravitational lensing. We have a diagram here, and Grant, I was wondering if you might be able to tell us a little bit about what gravitational lensing is, and maybe what we're looking at here.
Sure thing.
How it works.
So if you imagine a galaxy cluster as a contact lens, it works in a lot of the same way, in that if you imagine space and time as a big rubber sheet and put a big bowling ball on it, and then roll marbles past that bowling ball, the trajectory or the path of the marbles will change. A very similar thing happens in that the enormous mass of this galaxy cluster warps space and time around it. So light from distant background galaxies passing near this cluster, its trajectory gets bent just into these arcs that you see. So I mean, Karen and Jane work on this more directly, and they can also tell you some stuff about it.
Okay, we have one more graphic that's a little more illustrative of the stretching out effect. This just shows that there's something in the middle that's doing the bending. Here's another look. We have a distant background galaxy whose light is being distorted by the group of galaxies in front of it, and you can see that these arcs are being made here. Jane, you want to comment on that a little bit more?
I'm turning this one over to Karen.
Oh, I'm sorry.
Karen's very
This is going to
articulate.
be a fun hangout. I love this already. I love it.
Yeah. So right. So everything you said is correct, and sometimes this the galaxies are not only being stretched by the light, kind of like a funhouse mirror type effect. They're being stretched, and you sometimes would see multiple images of the same thing. So the light would start from a galaxy, go around the cluster, and get to you from one direction, but also some other ray of light that was supposed to go in a completely different direction would bend around the cluster and get to you as well. And this is what you're seeing here in this graphic. You see light from the galaxy going around the cluster in two different directions and gets to the Hubble Space Telescope image. And my job in this collaboration is to try to figure out what the optics of this gravitational telescope is. So we're using the cluster, which is far away in space, to magnify light from the background universe. So it's acting sort of like a cosmic telescope or a magnifying glass, which we don't know the optics for, and my job is to solve this problem and figure out what the optics are. And then we can, once we figure out the optics or the mass of the cluster that is responsible for the gravitational lensing, then we can use it to start studying the background sources. And now back to Jane.
Okay.
Back to you, Jane.
Back to me. Yes.
So I guess what blows me away about what you just said, though, is you said it in a kind of nonchalant way. My job is to figure out the optics in this, and once I figured that out, we can kind of tell which galaxies are which and things. How do you do that? How do you sort this all out? You've got these smudges in an image. Some of them are all over the place. Sometimes you have two images of the same galaxy in different parts. You've got this big old galaxy cluster in the middle doing all of the distorting. How do you sort it out? Where do you even start? All you have is an image, this thing.
Well, I start by staring at the image really, really hard, which is the best part of my job. I love looking at those beautiful pictures of space.
Well,
I think
kind of
if
like
we
a
didn't have
magic
pictures
eye
to look
thing,
at,
or what?
yes, you know how like you have that those back when we had newspapers, there were those
wait,
caricatures. Sorry, like
What's
actual
the
printed newspapers, and trying to look through them on Saturdays, and there would be like those two pictures that you have to match. This thing looks like this thing. It's sort of like a puzzle. So I look at the pictures and try to find things that look sort of the same. So they may look the same because they have very, very distinctive color. Maybe they look pink or green. Sometimes they look the same because they have very similar morphology. So they're kind of like, look like a spiral galaxy that's distorted in one way or distorted in another way. And when I can find 2 or 3 or 5 of those that look like they're the same, I can say these few objects are images of the same thing in the background. And I can use this information to try to figure out what sort of mass distribution could cause this distortion in space-time.
Wow. So you're kind of doing the one of these things is not like the other game for a while, and then you figure out, you match up some stuff from different parts of the image. From that, you try to figure out the mass distribution. Now, that's just a way of saying where all the mass is in the cluster and how it might be bending the light, and then you do.
Right. So we have a pretty good idea of how the mass bends the light, and this comes from Einstein's relativity theory. And we have a set of equations that we can use. We know how physics work, and when I plug those, it sounds kind of simple, but there's a lot of physics behind it. I can put those constraints in the equations and try a whole bunch of different models or different math distributions and find just the right one that gives me the correct answer.
Okay, so let's go on to the. So that's a little brief idea of what gravitational lensing is. If you got any more questions, please, feel free to drop us some notes in the comment box or whatever, and we'll try to get to them to clarify things. But I want to get on to the observation. Grant said that this was you guys' thing. You guys took the data. Is that correct? So who wants to tell me about the story behind why you did this, and who decided to point Hubble at this thing and look at the data, and then you found this very surprising thing that wasn't there before? I'm going to say thing a few more times. How about you, Jane?
Sure.
Go ahead.
So this cluster is one of 37 clusters that we propose to observe with the Hubble Space Telescope. And there are about 70 bright big blue arcs, like the one in this cluster, that are the targets for this proposal. So the way Hubble works is that if you have a really good idea, you write a proposal, and if it beats 9 out of 10 other proposals, you win.
More on that, see last week's hangout.
Right?
Right over it.
And it's deadly, right? It's 90% rejection rate. There's very few things that we do in our lives where we have a 10% chance of succeeding. But writing Hubble proposals is one of them. So that was last week. So we wrote this proposal because we wanted to both understand where the mass is in clusters, and understand clusters of galaxies better, and this is a way to probe dark matter. I mean, Karen's saying it so cavalierly, but what she does is figure out where all the dark matter is, right? I mean, it's one of the few ways you can actually see not what dark matter is, but where is it? How does it behave? But we also wanted to study these background galaxies, and that's my particular interest, is that I want to study how galaxies evolve, and galaxies. The universe is annoying in that galaxies are faint and far away, and hard to see.
That just says the universe is annoying.
It's really annoying.
The universe, it is annoying, right? The telescopes we have that we've been able to build, galaxies that are far away look faint, fuzzy, and tiny, and you just can't study them the way you really want to.
It's very inconvenient.
Well, in my other job, I'm working to build the James Webb Space Telescope, so we are working to build bigger and better telescopes, but being impatient, I don't want to wait, so using these natural telescopes is a way to, for small parts of the sky that are lucky that there's a galaxy cluster in the way, you can study the background universe, and you get these magnifications. So it's like so it really is a natural telescope in front of your Hubble Space Telescope.
Yeah, we've talked about that a lot with Frontier Fields. They're doing the same thing.
Yeah, right. So that was our hook. That was the argument. We have 37 fields on the sky that our team has found. They're really good lenses, and so we want to take images with Hubble and study background galaxies, to study the universe at high spatial resolution, basically to do illegal things. To be able to see sharper images that Hubble can normally see, and to see fainter objects that Hubble can normally see. So that's the program. That was the project, and this is one of 37 clusters that we got data for. So it was a 107 orbit program, which is a big but not huge project for Hubble. We submitted it 3 times. So to get it accepted.
All right.
Yeah, and then on the 3rd time it was accepted, and we got the observations, and the observations just finished a couple months ago. So all 37 clusters have now been observed.
Yeah, Carol, I just wanted to ask you real quick. Sometimes when you're doing a Hubble proposal, it isn't always about the science itself, is it? I mean, sometimes it's about the timing. Sometimes the science is good, but there's so many proposals that you can't always work it in.
That's true, and so the panels have to take a look at that and try to, because I mean, in the early days, there were probably some proposals that weren't great. Now all the proposals are great. We know that going in. So it's trying to balance, the different fields, exoplanets, the cluster lenses, stellar populations, all that kind of stuff against each other. And lots of times people put in a proposal and they might not get time, but they get magnificent scores. It's just we only have so many orbits, as we talked about last time. We only have like 3,000 orbits. I was going to comment that, you know, what you're hearing is that you're getting a lot out of these observations. You're getting understanding the orange galaxies that you see. What is that cluster? What kind of galaxies make up that cluster? Then you're finding out, oh, something about those background galaxies because they're lensed. And then when you build the lens, you say, well, there's a lot of mass in those orange galaxies. Let's start with that. But then you have to add the dark matter because that's what really makes up this lens phenomenon. So you're learning, you know, all those things. And then, lo and behold, they saw this chain, and they went, oh, well, there's something else we're learning about.
Yeah, well,
just from this one image. So it's a lot of information, and that's why you need this marvelous team to work together, because each person has expertise in some other thing, and they're interested in a different aspect of it. And that's what makes these fields very rich, because a lot of science comes out of it.
If you pull up the picture that you showed before.
Well, okay, go ahead. Kelly, can you put that first one up that we had? That of the galaxy cluster itself.
Of our cluster, okay, which we'll call 1531 in short, because we don't want to say the entire phone number thing. So what drew us into this cluster, as you can see, is like that ring of stretchy arcs around the center, which from the ground kind of just looked like a ring. So from the ground, meaning from ground-based telescopes, we had nice images from Gemini and Subaru and other telescopes. And so this is a great lens. This is a fantastic cluster lens.
Because it's so round, the features around it are so complete. Is that why? Or
yeah, it's very certain that this is a gravitational lens, and it's magnified, and we can study those background sources, and you can see a lot of little emission clumps, like little knots, blue knots on the ring itself. So this is fantastic for our science. So we also saw some blue stuff at the center, which we thought was maybe also some part of the lensing, but we couldn't really resolve it. We couldn't see it well from ground-based observations because they're so blurry. And then we pointed the Hubble Space Telescope at it, and we said, you know what, this is a fantastic lens, just like we thought it would be. But wait a minute, what's that over there at the center? What is this?
Yeah. Okay, let's put that up. Let's go ahead and put that up. We have a blow-up of it. Here we go. Here's a slight blow-up of it, and we have an even closer one coming up. So, yeah, you're talking about this stuff in the center. There we go.
Right, exactly. So all that stuff in the center, what is this? This cannot be I'm looking at this, and I'm saying, this is not lensing. This is not a background galaxy that's being lensed by the cluster. It's way too bright to be a background galaxy that's being lensed by the cluster.
Space unicorns. Gotta be space unicorns.
Right. And such a thing should not exist in a cluster.
When I looked at this image for the first time, not being an expert, I don't work on gravitational lensing like Karen and Jane do. I saw this and said, well, this is unlike any star formation in field ellipticals or in cluster ellipticals that I've ever seen. So this has to be a gravitational lens. This would be some really crazy gravitational lens, and that's really exciting. But that was my first hypothesis. And so we ended up independently ruling that out in two different ways, both with ground-based spectroscopy and with Karen's paper, which goes through full detail explaining how this could not possibly be a gravitationally lensed image. And so what you're left with is this amazing result that this is actually star formation taking place within these two colliding giant elliptical galaxies.
So Karen, can you give us some idea why you're so sure it's not lensing?
Oh, so in gravitational lensing theory, you can, once you make a model of the cluster, once you understand the optics, like I said, you can make predictions of what other images of the same source look like. Sort of, let's say you have two mirrors in front of you, right? One to the right and one to the left, and you see an image in the left mirror. You can sort of predict what that image would look like in the right mirror, right? Mm-hmm. If it's, you know, rounded or some color or some features in it. And this is sort of what the lens model can do. You start with one image and you can solve the equations and figure out what the other image would look like. and the other image looks a lot fainter than this. The image that would appear if it had appeared at the center of the cluster would be so faint, it would be fainter than the faintest blue thing that you can see here.
So the blue stuff that we're looking at that is so bright here would appear fainter.
If this was a lensed background galaxy right here, this would be very, 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 very faint, probably 200 times fainter than this.
Okay. So based on your models are telling you this can't possibly be much brighter. So okay, you've ruled out that this is not lensing. Then what'd you do? Stare at it some more?
What?
Then we call our friends.
Who knows about this? Who could write a paper on this? Right?
Yeah.
Exactly.
What is this stuff?
So what we're looking at. So you see the yellow stuff.
Right.
Two bright yellow clumps on the left and right. Right. These are the nuclei of two giant elliptical galaxies that are crashing together. And when I say giant, I mean huge. Together, their projected stellar envelope is about 300,000 light years from end to end.
Compared to our Milky Way, which is?
About 3 times the size.
Okay.
Okay. So these galaxies are far along in the process of crashing together. You can see that their nuclei haven't exactly coalesced yet, in that you can still see two independent clumps. But then you see this blue squiggly stuff in the center, which we just talked about, we ruled out could be a gravitationally lensed image from a background source. And we've also ruled out that it could be some weird projection effect from some foreground source, meaning all of that blue emission that you see is embedded inside the yellow emission from the hundreds of billions of stars associated with these two merging elliptical galaxies.
Yeah, so there's kind of a halo around this a little bit, around the two nuclei. You're talking about that, right?
Yes.
This very thin, orangey, wispy stuff around the two bright.
Exactly, and the two elliptical galaxies actually extend far beyond where this image shows. So this is like taking a magnifying glass and zooming in on the center.
Okay.
So the galaxies themselves are about 3 times larger than this image, and we're looking at the sort of central 100 kiloparsecs or so. So the blue squiggly stuff that you see in the very center is 100,000 light years from end to end. And after confirming that indeed this had to be blue excess emission from star formation taking place within these galaxies, this spurred us to do a lot of follow-up observations to figure out what is going on here. So what we think this is, you know, when you have coffee and you're stirring it, and you pour milk into your coffee, for a little while you see ribbons of milk start to spin around, but then the milk sort of evens out and your coffee just becomes lighter, creamy coffee, right? Mm-hmm. What we think this is a very serendipitous, lucky snapshot of a very short-lived morphology for this star formation. So all of this blue light that you see is about 5 solar masses per year worth of new baby stars forming, and 5 solar masses per year. So 1 solar mass per year is roughly 1 Earth-Moon per second of mass. So this star formation is equivalent to about 5 moons per second worth of new stars being created, about 5 solar masses per year, which is a lot of star formation, by the way. The Milky Way, for example, is slightly less than 1 solar mass per year, right? And what's amazing is that elliptical galaxies, like Jane was talking about earlier, generally, not always.
Never do this. Yeah, they never do this.
Yeah, no,
well, maybe we should back up and say why that is. Let's say why that is. Elliptical galaxies are typically very old galaxies, right? I mean, they're among the largest in the universe. So why don't that explains their color, but why aren't they having new star formation?
So
typically.
So what's weird about the universe is that it exhibits big to small behavior in what should be a big to bigger universe. So in our universe, things are hierarchical, right? Things grow by the coalescence of ever larger clumps of stuff, right? Mm-hmm. And so, if star formation followed this trend, the largest galaxies in our universe would have the most booming star formation rates, and yet we see the actual opposite effect. So it turns out that you actually need to actively truncate or kill off star formation as the universe evolves. Which is a whole lot. That's a whole. So
wait. You're saying as the universe gets older and all these galaxies collide more and more, they get bigger and bigger. You're saying we should be seeing higher star formation in these galaxies, not lower, and yet we're seeing lower. So you're saying something must be truncating. Something must be saying stop. don't make any more new stars.
Yeah, various forms of energetic feedback have been invoked to explain this. Feedback from accreting supermassive black holes, feedback from dying stars, from supernova, and things like that. And that's a subject for a whole other Hubble hangout.
Agreed, I agree.
Yeah, the short version is it's a case where we see something happening in the universe, which is that that galaxies in clusters are red and dead, and astronomers spend a ton of time trying to make it happen in theory.
Yes.
Right? So we spend a lot of time trying to figure out how do you keep elliptical galaxies from forming new stars? How do you keep it, how do you truncate the star formation in the first place so they're done, and then how do you keep them from making any more? Because if they make even a little bit more, they turn blue again, and that's not what we see. So this is a different topic. But crushing star formation in elliptical galaxies is a thing that a lot of people spend a lot of time trying to figure out. How does the universe do it? It obviously is doing it. We don't quite know how.
So one way we can get it to start up again is to collide, to push them together, it looks like, right? Is that what we're seeing here? So we're on a related question with Adam Synergy from the Q&A app. So let me just go ahead and put this up. He's asking, is the gas fueling this burst of star formation burst of star formation believed to originate in these elliptical galaxies, or does it come from a shock wave linked to the merger, or perhaps from elsewhere? So you want to elaborate a little on that?
That is an absolutely fantastic question. That's actually that is a fantastic question.
Adam's one of the he asks a lot of great questions.
Yeah, well, go Adam. Yeah. So first of all, we think of stars as incredibly brilliant and energetic things. But what's kind of weird is that you need to form stars out of puddles or reservoirs of super, super cold gas. So if you want to form a star, you need to take gas and cool it all the way into these puddles or lakes or reservoirs of what's called very cold molecular gas. We're talking tens of Kelvin, so super, super cold, dense stuff. And then from there, you can get core collapse and growth of these baby stellar seeds, and then actually start to form stars. So one of Adam's excellent question is a very pertinent one. Was this molecular gas that is now forming these stars already in the galaxies before they crash together? And has the collision of the galaxies sort of stirred up this molecular gas? So like water in a bathtub, which is just sitting there. If you have them, I don't know, you crash the bathtub into something else, you get waves in the bathtub, and do we form stars now along these waves? Or are we continuously raining cooling gas from the ambient hot X-ray halo that surrounds these two galaxies? So I've skipped a step there because, yes, giant elliptical galaxies sit in a bath of ambient plasma, tens of millions of degrees hot. And very often when the central density of this plasma is high enough, that central plasma can cool very rapidly. We're talking on 300 million year timescales, which to an astronomer is a very short timescale.
Cool enough to form stars?
Yeah, so to address Adam's question, these stars could be forming amid molecular gas that was already in the galaxies to begin with and has now just been stirred up because the galaxies have collided together. Or this could be like a slow rain of cooling gas from the ambient X-ray atmosphere that forms puddles, and the merging process is associated with huge gravitational torques, enormous amounts of shear. And so maybe this rain is falling into this rather violent process of two galaxies coming together, and that's what creates this really bizarre morphology that we see in the star formation.
Material that you were suggesting, is that an explanation of the other?
Hey Tony, I think you're going through a black hole right now.
Yeah.
Yeah.
Oh, sorry.
Tony's being gravitationally lensed.
Yeah, we're getting spaghettification of your data stream.
Yes.
Can we fix that?
Yeah. Okay. I don't know what to do to fix it.
Put something on the chat and we can ask the question.
Okay.
Yeah.
All right.
We'll speak for you.
Hello, am I back yet?
Yes.
You're sounding much better.
Okay,
yeah.
Good. So my question was, I think the press release indicated that it might be more of a rain of material explanation. Do you have a preference over one of these explanations over the other?
Yeah, so our initial look at this cluster formed 3 basic hypotheses. To test all of these hypotheses, you need follow-up data. So this could very possibly be a rain from the hot X-ray atmosphere, but we won't know until we get a Chandra X-ray observation of this source, which has now been approved. It was approved last month, and it will take place sometime during this year.
Okay.
So Chandra will look at this thing for 130 kiloseconds, which is a number of days, I think, or almost, it's quite a while, 130,000 seconds.
Yeah.
It will stare right at this source, and we'll get an exquisite high-resolution X-ray image, which we can then overlay on our beautiful HST image, and we can do a multitude of tests. So we can do spatially resolved spectroscopy to get the temperature of the hot X-ray plasma, and we can do density, entropy, pressure maps. Those are buzzwords for what ultimately is. We'll find out if this could be a waterfall of cooling gas from the X-ray atmosphere, or a shock in the colliding hot X-ray halos between these 2 galaxies. If you collide 2 galaxies together, you also collide their 2 halos together. So maybe you're colliding their 2 hot X-ray plasma halos. Then you create this high-density sheet of X-ray gas between the 2 galaxies. And when you increase X-ray gas density, you also increase its cooling rate. So the very act of these galaxies colliding together could have set up kind of a waterfall, a sheet of cooling gas between the galaxies. And then what you're seeing in this blue emission is like rocks at the bottom of the waterfall. This sheet of cooling gas forms these puddles of cold molecular gas, and then this is where you form the stars. So that's another hypothesis that we can test with this follow-up data, this X-ray data.
So as usual, it's always more observations are needed.
Yes.
Yes,
Exactly.
for sure, as always. So good. I look forward to hearing more about that when Chandra is able to look at it a little bit as well. Now, this is something that the press release called a beads on a string feature or phenomenon. And while it seems to be unusual in elliptical galaxies, it's not so unusual in galaxy collisions in general. Is that correct, Jane? Or should I ask Grant? Can you hear me?
Yeah, Grant, why don't you take that one?
Oh, okay.
Okay, sure.
All right.
Yeah, so what you're seeing here, so if you can see the image, what you see are not only blue filaments, but you see clumps along these filaments. And these clumps appear to be, at least in projection, relatively equally spaced from one another. So it kind of looks like a pearl necklace that's kind of laid out on a table, right?
Okay.
So this is not something new. So in 1983, a group of astronomers were looking at images of spiral galaxies, and they published a paper saying, hey, if you actually look at the arms of spiral galaxies, star formation in those arms doesn't happen in uniform filaments, it happens in equally spaced clumps. And all of these clumps appear to be separated by about 1 kiloparsec. 1 kiloparsec is about 3,000 light years. These clumps appear to be separated by 3,000 light years from one another. So they term this beads on a string morphology. And it turns out that this is not actually it's profound, but it's not profound in the sense that it's that surprising, because it's really just a kiloparsec scale manifestation of something called the gene's length, which is related to the gene's instability, which would be another Hubble hangout to talk about, but you can think of
But in 10 words or less, you have to tell us. No?
Yeah. So in 10 words of less is this. Rain falling from clouds in the sky doesn't occur in continuous filaments that are unbroken from the ground to the sky. Rain falls in drops. Why does rain fall in drops? Because a cylinder of fluid will prefer to contract into a series of droplets just because those spherical droplets are a lower energy configuration. So just like...
Wow, that was outstanding. It was more than 10 words, but it was really a great explanation.
So I want to be careful here for our more advanced audience like Adam, because Adam's about to complain. Yes, the gene's length it does involve a bit slightly different physics, but when you actually boil it down to the fundamental processes of what's going on, the physics that dictates the morphology of this star formation is not much different from the reason why when you turn your water faucet on in your kitchen, really slowly, the water will contract and fall into a series of droplets by the time it reaches the bottom of your sink. It's the same physics.
I have a question, actually, but it's not exactly what you were talking about. It wasn't about Jean's length. You were talking about the two elliptical galaxies and the fact that they may be merging and or they may be getting material rain down on them, and you were talking about the morphology of the halos. In the image we are looking at right now, it doesn't look like a double-lobed halo. It looks like a single spherical halo. And if you go back to the larger view, it looks like the ring of arcs is actually at a slightly different orientation, but it does encircle. It does encircle those two objects. Is that completely unrelated? I mean, that is the mass distribution that's causing the lens, and it's also the mass distribution plus maybe gas that's causing the star formation. Does one tell you anything about the other?
Turner, Jean?
Yeah, so first of all, don't let the appearance of those arcs trick you to thinking that the mass is distributed in the same direction as those arcs. It's not necessarily always follow.
Mm-hmm.
In this particular case, the mass is aligned along the line that connects those two galaxies to each other, at least in projection. So the cluster is elongated in the direction of the merger.
Okay.
Okay, thank you. So I got a couple of good questions here on the Q&A app. Let me bring one up here from Eamon Fanton. He's going, optical lenses have a focal length. If the hidden galaxy is exactly at the focal length, would you get a perfect image of that galaxy? So I guess he's asking, is there a configuration, a way in which we can look at these lensed galaxies which would be perfectly in focus?
Yeah, so there is such a thing, and it's called an Einstein ring. And this usually would happen when there's a very simple lens like one galaxy that is very massive, and an object like another galaxy that is exactly behind it. And then instead of getting, let's say, 2 images of the same thing or 3 images of the same thing, you'll get infinite images of the same thing, and that would form a perfect Einstein ring. There are a lot of examples of those things. This usually doesn't happen in clusters because they are very complicated. There's a lot of mass, and the distribution of mass is not just one object.
Yeah, we've talked about that at length with our Frontier Fields Hangouts.
Right. Like here's an example. Of,
Scott's showing an example of one of the lensing models that they're using for Frontier Fields, and this would be sort of what you're describing, Karen, with the optics. You know, the mathematical representation of what are the optics of this system. This is one of the Frontier Fields models, but this, as you can see, they're pretty complicated, right? Do you want to comment on this just a little bit, maybe?
Yeah, so clusters of galaxies have galaxies in them. They also have a lot of dark matter, and they're actually nodes in the cosmic web of things coming together. So unlike one galaxy, which could be very isolated from the rest of its environment, this really feeds on dark matter and gas and galaxies from the entire cosmic web. So it's not very smooth and symmetrical looking. Sometimes it could look like this picture that you have on, kind of like a weird amoeba thing, right? So it's more complicated.
Yeah. So these things can get quite messy when it comes to galaxy clusters. Okay, Hugo Burnham, he's always great. He's got a comment here. 130K seconds equals 36 hours plus change.
Thank you. I'm doing math in my head and like, that's not happening.
There you go. So yeah. So thank you, Hugo. I was off. We appreciate your helping us out there. I have another comment also from Eamon Fanton. Will gravitational lensing affect the redshifts of the objects being lensed? What are the implications or uses if redshift is affected? Can the distance to the lensed galaxies be measured accurately? So there's 2 questions there. One is, does it affect the redshifts of the object being lensed? And the other is, can the distance of these lensed galaxies be measured accurately? Who wants to take that one?
Yeah, so the redshift is something that you measure, and it has to do with the expansion of the universe and how the galaxies that seem like they're getting farther and farther away from us, the wavelength of the light that comes to us becomes redshifted. So this is something that can be measured, and it's not affected by gravitational lensing. The distance can actually be measured from gravitational lensing because the geometry of the lens, or how powerful the lens is affected or is related to the geometry. So how far the lens is from you, how far the background source is from you, and how far the background source is from the lens. So all those three distances. And yes, you can independently measure the redshift and measure the distances. And this can, in theory, give you information about the cosmology and about the geometry of the universe.
Great. Good question. Thank you, Amy. That was good. So Judy Schmidt has a comment. Those J1234 plus blah, blah, blah names are just shorthand coordinates. As a layperson, I just wanted to mention it because it's a simple thing that is not obvious but helpful to understand why they are named like they are. That's correct. They're mostly just coordinates.
Thank you.
So thank you for that, Judy. That's an important thing to point out. And here's one from Ban Qasim, I think. And this maybe this one's for you, Grant. I don't know. Where does all energy go inside a black hole exactly?
Exactly.
Exactly.
That is a very good question. First of all, you can't grow a black hole for free. So when you dump matter onto a black hole, you also, at the same time, liberate an enormous amount of gravitational energy. That is why you see things like radio galaxies and quasars and things that I'm sure you've talked about in other Hubble Hangouts. Mm-hmm. Where the energy goes within a black hole is absolutely a subject that would be actually a very nice hangout. Mm-hmm. That's a very long and complicated answer.
Okay.
We'll have Jane answer that one. She's way more elegant than I am.
Well, I would say that energy is mass and mass is energy, and once mass goes down the point of no return of the black hole, it's gone. It's not accessible, and the same is true for energy. And at some level, that gets into a philosophical question: is it still in our universe then? Right? If you can't touch it, if you can't get it back, it can't even send you a signal, right? It becomes causally disconnected from us.
Yep.
Yeah. So, but that
I think
energy went down.
It's important. Sorry. Go ahead.
I was just going to finish the thought that because of mass-energy equivalence, energy that does get down there adds to the mass of the black hole.
Yes.
So when we talk about a black hole that weighs 1 billion times the mass of the sun, that you could equally say it has that much energy, right? That's just how much stuff is in there.
Okay. I have something from YouTube now. This is Craig Landon. He's asking, and I have it up on my screen here. Could this be an event similar to the bullet cluster collisions with dark matter halos colliding?
Yes, that is absolutely a fantastic question. So I guess we don't have an image of the bullet cluster.
I got you covered. Hold on, just
Scott's driving the internet for us.
Oh yeah.
Let's get a okay. So there's a combined HSC and Chandra image of the bullet cluster. To answer your question, so not only do galaxies merge together, but clusters of galaxies also sometimes crash together too. This absolutely could be the late stages of a cluster-cluster merger. What we could be seeing is that those two colliding galaxies at the center of this image are actually the heads of two smaller colliding clusters of galaxies. There's a bit of evidence for this in the redshift distribution for galaxies in the cluster. You see what's a bifurcation in redshift space, meaning a slight bimodality in redshift space for only about 13 of the galaxies in this cluster. So we're talking about low statistics and therefore low confidence in that hypothesis. But this could absolutely be the late stages of a cluster merger, kind of like what you're seeing here with the bullet cluster.
Yeah, Scott's got it up now.
Yep, I think so. Okay, great. And we will be able to test this hypothesis with a Chandra observation and with follow-up observations from the ground. For example, if we get optical spectroscopy for many more of the galaxies in this cluster. We can more accurately map the redshift distribution and therefore kind of sculpt out the 3D geometry of galaxies in this cluster and try to work out what's happening here. This absolutely could be a cluster merger.
Well, why don't you give us just a real quick description of this, what we're looking at with the bullet cluster here?
Yeah, so let me pull up Scott's image so that I can...
Yeah, just click on it there.
Yeah, exactly.
Yeah.
So the bullet cluster is like that famous picture of a bullet going through an apple, right? So two massive clusters of galaxies that were once relatively independent have crashed together, and one has now passed through the other, just like the bullet, that slow motion bullet through an apple. It's a very famous image, right?
Yeah.
And what you see in that kind of V-shaped or L-shaped pink material off to the right, I guess that's kind of obvious, right? Mm-hmm. That is a shock in the X-ray gas that has been associated with this bullet, this much faster cluster, plowing through at very high velocity this more massive cluster that you see to the left. So it's taken one full passage through the cluster, and it's created this sort of shockwave in the X-ray gas that you see in pink there.
Nice. All right. Very good.
So, Grant, I'm really glad that this question came up, because if you look back at our cluster 1531, the lens model. Sorry.
That should be up already in the.
Yes, that's up. Mm-hmm. So, Grant, the lens model does indicate that there's more mass to the, southeast, which is the left-hand side of this picture.
Yep.
So the lens model does want this cluster to have mass in that direction, and that could indicate some stages of merger or past merger that happened.
Yep.
So we should talk about this more. Yeah.
The three of us are going to have fun when we get this Chandra observation.
Sounds like it. Yeah, that sounds like we should check back in with you guys too to see what develops out of that, because that sounds like you're going to be able to answer some big questions with this. So here's one from Dan Buddha on the question Q&A app. If the galaxies are getting far and farther away from one another, why do we have clusters? So if all the galaxies of the universe is expanding and getting far away, why are there clusters?
Well, in some places, the expansion of the universe can overcome gravity. Gravity, if things are very, very massive, they just gravitate towards each other and create very massive objects that just decouple from the expansion of the universe. So
Right.
they, in some sense, they don't expand with the universe. Kind of like the cells in your body. They stick together with other forces, and they don't expand with the universe.
That's right. Although I think Scott's head expands with the universe. So yeah.
Well, it's accelerating at least. I don't know at what rate.
Expansion is accelerating, correct?
Right.
So that's a good point. I mean, even though space-time is getting, there's more of it, and it's getting further and further apart. These galaxies the universe is getting further apart. Locally, sometimes when you have big clumps of things together, like a bunch of galaxies, their gravity is not overcome by this expansion. So that's a good distinction. Thank you for the question. So let's see. Michael Jobin is going, could the dark matter in the galactic barrier, could dark matter be the galactic barrier mentioned in Star Trek? Oh, yeah, sure. Sure, I'll take that one. Yeah.
Oh, I was going to take that one. Is that going to turn my eyes white and
yes.
No,
I
totally
develop psychic powers? Because that would be great.
Yeah, it would be cool.
I could
Can
write
I be
papers
Q then?
faster.
I'm going to be Q.
I'll
if
say you
that's
figured
what
you
we're
want
doing.
Q. What is it?
Absolutely.
Yes, you're expanding head space.
Right.
Expanding head space. Okay, we're getting a couple more here on the Q&A app. Here's one more. Here's one from Tom Conlon. With those two colliding ellipticals, could the blue stuff in there be superimposed signals because they are near the same line of sight and not actually colliding? That changed the detection from orange to blue. I'm not sure how to...
Well, no, I think...
You understand that? Okay.
Yeah, so that's actually a fantastic question. So everything we see on the sky is three-dimensional stuff that's been projected into two-dimensional space. So we're really watching a universal puppet show in shadows, right? A shadow hand puppet show, right? So it's very important that when you're looking at a 2D image, you understand the 3D structure of what you're looking at. And so when we got this HST image of the cluster, this Hubble image of the cluster, one of the first questions you ask yourself is, well, am I just seeing a projection effect of stuff along the line of sight? Maybe all of this blue squiggly stuff that we see in the center is completely unrelated to these two galaxies, and maybe it's just sort of in front of me, or even, as we were talking about earlier, behind the cluster, and maybe it's a gravitationally lensed image. So this is one of the first things that we tested, and we're able to rule this out. So we ruled out this possibility with ground-based optical spectroscopy, which means you take the light from this cluster and turn it into a rainbow. You disperse it. And you can see things like emission lines. One of them is called H-alpha, for example. And you see emission lines mapped to a certain redshift. Redshift is just the way astronomers think about the 3D structure of space, right? You can think about distances from you in terms of redshift. And it turns out that everything that you're seeing in that image, in the central regions at least, meaning the two giant yellow elliptical galaxies that you see, and the blue squigglies, everything is exactly at the same redshift, which means that this can't be a 3D projection effect from stuff along the line of sight. And indeed, everything needs to be basically on the same plane, so the two merging galaxies indeed are merging and are deeply embedded in one another over 60,000 light-year scales, basically. And the blue squigglies that you see indeed are embedded in the stellar halos of those two merging galaxies. So this is not a projection effect, but that is a great question because it's one of the first that we asked. It's very important. Yeah.
Yeah, that was a good question. Thank you, Tom. Well, I'll take one more, then I'm going to ask Scott if I'm missing anything. Here's one from Julio Cesar Brito from the Q&A app. What makes the Milky Way center take a bar form, and can it be the jets of a supermassive black hole? Anybody?
So I can take that.
Okay.
The black hole at the center of our Milky Way is a slacker. It's really disappointing. As someone who likes active black holes and galaxies, I continue to be disappointed by the Milky Way. So if the universe is annoying, the Milky Way's black hole is just disappointing.
Sagittarius
right? Why? Sagittarius
Plus, it's in the way to everything else.
What?
Plus, it's in the way.
Yeah. I mean, I'm glad I'm not being continually irradiated, but you know, it's so dinky.
This is the grumpiest hangout ever.
Right? Sorry. So the proposals.
High bar, James.
Right here. First astronomer problems.
So this is a serious. So the serious problem is that there's tons of gas in the center of our Milky Way, and there's a black hole. There's a several million solar mass black hole, and yet the black hole refuses to perform. It's like when I ask my kid to say bubble, he just looks at me. He's like, I don't perform, Mom. No. Our Milky Way black hole doesn't feel. So it's got, you know, it's massive. It's in the center of a whole lot of gas, and it chooses not, for interesting reasons that we don't really understand, to eat any of that gas, or at least not to be very, so it doesn't have big jets, and it isn't bright, and it's really faint. You have to observe with Chandra for days to get a signal. So that's a long way of saying that the Milky Way, our black hole, is so underperforming that it's not really capable right now of doing much of anything to change the structure. In the past, if it was more energetic, there are these neat Fermi bubbles that show that in the past, the black hole at the center of our galaxy shot these big bubbles of gas out through the galaxy. The spiral, I'm not quite sure about because it's wrong. I have to think about that.
Yeah. So, but didn't I hear something about a stream of gas in the center of the Milky Way that's like heading towards the black hole or something like that? Or am I thinking of something?
Yes.
Soon something might be happening, right?
Soon something might be happening. That is the story of the universe, right there. Maybe, you know.
There is a small gas cloud which has now passed behind Sagittarius Star. Sagittarius Star is the name, our very prosaic name for the black hole in the center of our galaxy. Right. There is a small, I think, million solar mass or 100,000 solar mass cloud of gas that has passed around and is coming back toward us around Sagittarius Star. So it's a small gas cloud. It apparently didn't accrete, and it also apparently didn't shear apart in the way that astronomers were expecting.
Okay.
In that it,
That's new.
Again, another disappointment for Jane.
Yeah.
Nothing interesting happened. It just went around.
It's still it's still an amazing result. These are papers by Stefan Glesson.
No, I know. It's a
but yeah,
good science, but disappointing.
Yeah. Oh, okay. So that's been new since I heard. I knew it was discovered and there was a possibility that it might go into the black hole, but it sounds like that's not going to happen.
Well, it remains very exciting, and indeed this is something that but when we're talking about accreting supermassive black holes, we're talking about things that are orders of magnitude more massive than the black hole in the Milky Way. So the Milky Way black hole is about 4 million solar masses. Mm-hmm. The black holes at the center of these two merging elliptical galaxies might be on the order of 1 billion solar masses each.
Oh wow, that is wimp. You're right. You're right, Jane. We have a pretty wimpy one then.
Mm-hmm.
Those.
Even for its mass, it should be punching harder.
It should be. Get a job.
Even in its weight class, it is just.
God, I can't believe we.
You're gonna give it an inferiority complex, and then something terrible is going to happen, and it's gonna shoot right at us. And I'm gonna just message you on Facebook. I'm like, Jane, look what you did.
Yeah. Move into our basement.
The Facebook will go down, so that's all right.
That's right.
True.
Facebook will go down.
The internet will have been gone, and probably Earth.
All right.
So yeah.
So Scott, if I missed anything, is there something else I didn't catch?
No, there's been a lot of just great tweets going on from everywhere. Not really questions, but a lot of just really great commenting on what people are learning, all on Twitter using the Hubble Hangout. So I do recommend those watching this later, go to Twitter, just look up the Hubble Hangout hashtag, and you can see the great conversation going on with it.
Right, good point. Thanks for pointing that out. Hugo, dude, I love you because he goes, we live in a lazy galaxy. What can you do other than keep looking up? That's right.
Ooh,
just like downtown, Tony.
Just like downtown. Right. Thank you, Hugo. Okay, well, I guess with that, it's our time is more or less up. Unless, Carol, do you have any parting comments or anything you want to say, or Scott?
No, I'm so depressed now about.
I know. I'm a little. We're gonna have to take a moment and maybe think about
really dark
job.
I was so excited to see Jane in the longest time, and now I'm just like, wow.
Oh, gee.
Such a downer, Jane.
She has a really high bar for performance.
She does. You have high standards. So let's flip that around. It's not that Jane's disappointed easily; is that she is up there.
Yeah.
And she has high expectations.
That's right.
High standards.
But even Jane was
love you, Jane.
by this image.
Yeah, this galaxy is not underperforming, right?
This one impressed Jane, so.
Yeah.
Right.
All right, I want to thank you guys. Thank you, Grant. Thank you, Jane. And thank you
so much,
Aaron, for joining us. This has been a great hangout. This was really interesting stuff. I kind of want to reconnect with you guys once you get the Chandra observations so we can see what you learned about this cluster and this particular string of pearls, what it might be and what it might be doing to us or them or the galaxy in general. So next week last week I misspoke when I said that our hangout this week would have been about the hot Jupiters and water vapor that was stored on them. It turns out that is going to be next week's hangout. So we will be around next Thursday, same bat time, same Hubble time, same Hubble channel, where we will be talking about hot Jupiters and water vapor and observations with the Hubble Space Telescope. So thank you guys all for watching. Make sure you bookmark it. I'll be making the event here later today, so we'll hope you'll attend. Carol, Scott, thank you as always.
Absolutely.
Great job. Thank you for driving the internet, Scott. You did a great
Thanks,
job. You might want to get that expanding headspace looked at. So
yeah, I just get bigger hats. It's
bigger. Oh, okay. That's one way to look at it. Anyway, folks, thank you all for watching, and as always, keep looking up.
Black hole feedback, so energy feedback from black holes. But on this particular study, I was very lucky to be sort of a guest in Jane and Karen's house because this is their data, this is their amazing program.
Okay.
They can tell you a little bit about it.
Okay. So wait a minute now. You said feedback. Say that again. Feedback from black holes. What kind of feedback?
Yeah. So I work on brightest cluster galaxies in the center of rich clusters of galaxies. So clusters of galaxies are giant groups of galaxies, which we'll talk about today. And I work on the galaxies in the very center of them. And many of these galaxies have what are called active galactic nuclei, so accreting supermassive black holes, billion solar mass black holes. And when you dump a lot of matter into a black hole, it liberates tons of energy. And I work on what effect that energy has on its ambient environment.
Good, because I wanted to clarify that, because it's a little counterintuitive. People think of black holes as just grabbing and sucking everything in, but they actually throw things back out again, too. So that sounds like an interesting hangout in and of itself. So that's great. Okay, how about you, Jane and Karen? Let's start with you, Karen. Is this your main area of research? Have you always been involved in galactic or galaxy clusters and collisions?
Well, I've been involved in galaxy clusters for as long as I have been in astronomy, but not necessarily what we're talking about today. So
Okay.
my main interest is in a phenomenon called gravitational lensing, which is the bending of light around very massive objects.
Right,
And
we're going to get to some of that in a little bit. So
Right.
we got some areas, we got some graphics for that, too.
Right, so like Grant said, we have this amazing project with the Hubble Space Telescope looking at galaxy clusters, which are very, very massive, so that they bend the light of galaxies behind them. And this is our main program with, or main science with this great program. However, sometimes when you take a lot of pictures with a space telescope, you find some things that you do not necessarily expect. And this object that we're talking about today is one of those things.
Great. Okay, Jane. How about, so give us a little background on what your research interests and background.
Sure. So I'm interested in galaxies of all kinds, whether they're forming stars or not, especially those that have black holes in their centers that are currently feeding and fueling, like Grant was talking about. And recently I've gotten very interested in studying galaxies using
KnowTheCosmos.com, and he's just getting started doing all kinds of cool things with the Natural History Museum in Los Angeles. So welcome, Scott. Welcome, Carol.
Hey,
How's it going?
Awesome.
You ready to rock?
ready to rock.
Do this.
Okay, so today, galaxy collisions. With me well, I've got 3 astronomers who've been using the Hubble Space Telescope to look at these things. I have, first of all, Dr. Grant Tremblay. He was, at the time the press release came out, was working at the European Southern Observatory. Now he is the NASA Einstein Fellow at Yale University. Welcome, Dr. Tremblay.
Hi, guys.
Also is Jane Rigby. I'm just doing this from left to right as they appear on my screen. Dr. Jane Rigby, she's an astronomer at NASA Goddard. Hi, Jane.
Hello.
And finally, we have Karen Sharon. She's a professor from the University of Michigan.
Hi.
Welcome, guys. Okay, galaxy collisions. You guys have been using the Hubble Space Telescope to study these things. Is this what you've always been doing, all 3? Is this your primary area of research? Grant, I'll start with you.
Well, first of all, I work on clusters of galaxies in general, namely star formation and...
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute. And today we have a really interesting hangout planned for you. We are going to be talking about galaxy collisions, and in particular, one galaxy collision that had some strange, unusual, bizarre things in it. And we've got the astronomers here to help us decipher what they're looking at and what they are. We'll talk about galaxy collisions and where they occur, and in particular what this strange feature that they found might actually be. And so we will be starting that discussion in just a minute, but before I start with the introductions, I want to say we're hoping you guys will leave us comments and questions on the Q&A app, which we're watching, the Hubble Hangout hashtag on Twitter. We're also we're looking at comments on YouTube and G+. So we hope you'll interact with us and let us know what you think. Give us some questions, and we'll get to those hopefully throughout the Hangout. With me to help with this hangout are my 2 good friends and colleagues, Dr. Carol Christian. She's the Hubble Space Telescope outreach astronomer, and also with me is Scott Lewis from
gravitational lensing, which we'll talk about. And so Karen and I and our colleague Mike Ladders and several other astronomers have this big program to study galaxy clusters that are really good gravitational lenses. And kind of by that's why we took this data. So it's one of 37 clusters that we wanted to study the background galaxies that are getting lensed. And this was a case, this paper that Grant, we invited you to our house. I like that. that came from was we were looking at this cluster and saying, wait a minute, what's that? Right? What is that? What's going on in the sun?
I remember we really did do this.
Right? There are pores, right?
Okay, so
Right?
let's go ahead and put up a picture of the cluster we're talking about. So you guys looked at this cluster known as SDSS, which I think stands for Sloan Digital Sky Survey,
Yep.
J 1531 plus 3414. I just love these names. So here is a picture of the galaxy cluster itself. How many galaxies are in this thing? Do we know?
Do we have to count right now?
Yeah.
More than
No, I'm
one.
just wondering if anybody knows.